Okay, Jim Bollinger again, NMH. Decided to make a video on the chain rule. I think it's hard to get a feel for it, and I'm hoping in this video, by the end of it, you'll get a chance to see why it is working and how it works. So I'm going to start with integration. I think you can understand the chain rule when you dive into what's taking place as areas under a curve change. All right, so much of math, it comes back to just the simplicity of rectangular relationships. For those of you studying in a sequential format, I'm going to have to lay out a little bit of a sense of integration so that we can get at the end result. I'm going to go around the classroom to try to set it up. Our goal is to get on that side of the classroom, and on the bottom you can see y prime is equal to h of g of x times g prime of x minus h of f of x times f prime of x. And I'm hoping that you can actually get a sense numerically of what's taking place. Okay, so if you want to fast forward to that section and if you get lost in integration, you probably can go right there to get a sense, but I hope that you follow it from beginning to end here. All right, so it all starts with a rectangle. All right, so integration, just a quick summary for those of you who are doing this sequentially. I start with derivatives and integrals day one. They're inverse operations, and I treat them as such. And so we begin the discussion on day one about what they are. And it takes a while to get a feel for integration, what's really taking place. So we're going to look at the area under a curve from A to B, place markers on the x-axis from A to B, and then we're going to change those values slightly. So we're really kind of heading towards the formal definition derivative, the limit as h goes to 0 of f of x plus h minus f of x over h. I'm sure you studied that by now if you're looking at the chain rule. So we're going to slightly change the area accumulation under a curve from one location to the next, and we're going to look at the change in area over the change in x. So in more formal sense, we're looking at the limit as h goes to 0 of a plus h, the second rectangle minus the first over the change in x. But what's going to change here is we're not going to take a number here, we're going to take a function. Let's say a plus f of x and b plus f of g of x. A couple of different functions for those place settings. And what happens then? Okay, so I chose what I hope are some pretty basic functions to work with. I'm going to let g of x equal x squared, so x squared here. I'm going to let f of x equal 2x, and we'll just look at the tripling function, and we'll look at how the area accumulates from 20 to 100, and then 20 plus. I picked 0.0001. Okay, so that's going to be our h heading to 0, just to get an approximate feel for what's going on. And so you're going to get one rectangle from 20 to 100, and then you're going to get another one, right? That's, in this case, slightly larger on the right, and we're losing area on this side, gaining it over here, and we're going to look at the net change divided by the change in x, just to get a sense of how that calculation is changing at an instant. So I plugged these numbers in. I squared this. Oh, there's a nice pattern to that squaring. So 100.00200001, and then we doubled this number, 20.0002. Okay, so that's our second rectangular area. Our first one was simply 20 to 100 under the tripling function. That was our first. And this is our change in x, 0.001. I threw it in a calculator, get an approximation of what's going on. And so the second area, our first area from 20 to 100 under the tripling function captured an area of 1,440 units. The next one, with all of the decimal stuff, came out to be 1,440.58800894. And now if we subtract those two areas, we can see this drops out quickly. we can get a feel for 4 decimal place, 1, 2, 3, 4. So that drops out. That's all about the limits of the study. And so it looks like we've got 0.5880 divided 0.0001. So at this instant, the conversion ratio is about 5,880 to 1. In other words, if we drew a tangent to the curve, it would be increasing at that rate. All right, so what's the goal here? The goal here is to, again, look at the chain rule. And we're going to get to it soon. So y equals some function with respect to another function, some composite. And the derivative is f of g of x times g prime of x. So where's that coming from? We're getting there. All right, so if you haven't studied integration yet, let me just say that area under a curve comes from, the rate of change comes from some position function. So this might be a velocity statement, position function. Maybe I shouldn't say that in those terms, but when we integrate this, we get this. I can explain how. You'll study that later. You plug in the values, and you come up with a function, which is this. All right, so we're going to take that derivative from this, it's not chain rule. We're just going to polynomial derivation. And it's 6x cubed minus 12x. And when you put 10 in, by God, you get 5,880. All right, now let's apply the chain rule and see what's going on. Okay, back wall, finally. All right, so we got the tripling function. We got this tripling function. We started at an x value of 10. And we're here. Oh, but we're really not at 10 anymore. We're really at 20. That seems to me to have a rate of change that's twice the rate of change of the normal y equals x. That's a 1-to-1. Y equals 2x. We're going down this axis twice as fast. So we're not in Kansas anymore. We're not on the x-axis anymore. We're on the 2x axis. And so if we look at that change from 20 to 20.002 with a change of 0.001, 0.0002 compared to 0.0001, our widths from, I'm going to have to make some width here, right? That's small. So this is going to be 20.0002. We're actually moving down this axis at twice the rate of how we would move down the x-axis in terms of our d-axis. This is twice that. And I'm not at 30 anymore for a height. I'm not at 30 anymore. I'm actually at 60, 3 times this number, 60. So if we want to talk about the rate at which we are losing area, we're losing it at a 120 to 1 clip. We're losing it. Now, what's happening over here? Well, we're not at 10 anymore because we squared it. We're at 100. But when I square that little change, I'm actually at 0.002 units of change, because this is the limiting factor. So this is 0.002. And when I divide that by 0.0001, I actually am moving down, I'm not on the 2x axis anymore, I'm on the x squared. I'm actually moving down this direction at 20 to 1. I'm really moving at 20 to 1. And I'm not at the number 100 because I'm on the tripling function. I really got 300 units of change here. Wow, that's 6,000 units of change. That's the rate at which that's changing. I'm gaining at that rate, at that instant area. And if I want to look at the net change, then I'm looking at 6,000 units of area minus 120 units of area. My golly, that's 5,880 units of area. So now let's apply the shortcut to this so that we can really see the chain rule. I think we're ready to see the chain rule. Yeah, so we're there. Remember, we're not in Kansas anymore. All right, so what was g of x? G of x was x squared. G of x was x squared, and h was the what? The tripling function. And so when x equals 10, boy, that's 300. Oh yeah, that's giving me this altitude. Yeah. And g prime of x, and g of x is x squared, and g prime of x, I'm sure you've studied that by now, right? G prime of x is 2x. And what was the x that we were, oh yeah, 10. And 2 times 10 means that this thing is changing at 20 units to 1, conversion ratio, minus f of x was 2x, I believe, yes? F of x was 2x, oh yeah. And so h was the tripling function. And when I put a 10 in, I'm tripling 20. Oh, that was this altitude. Right. And f prime of x, oh yeah, f prime of x, well, let's not put it there. That's where I'm going to put f prime of x is equal to 2. You know, linear functions, constant rate of change. So I'm moving in this direction at 2. Oh, there's our 120 loss and our 6,000 units of gain. Woo, net change, 5,880. So where's the final shortcut? Well, I think we dropped that into the tripling function. X squared into the tripling function. There it is. X squared into the tripling function. And then we did what? We took the derivative of g of x. Well, there it is. And then I subtracted, I think we dropped that, f of x, into the tripling function, times the rate of change of f of x. There we have it, the chain rule. Now, I assume that when we have more than, simple chain, then we're moving into more dimensions of geometric interpretations, which are harder to see and perhaps harder to grasp. But, once we see a simple level of change, we can imagine that there are more complicated ones, but they still follow the same rules, same mathematical principles. So that was my attempt to give you a little feel for the chain rule. Hope it helps. I'm not a math major. If I've broken any principles of mathematical play, feel free to write to me or correct them. But it seems to be what's taking place. So hope that helps. All right, take care. Bye-bye.